So today I have Linda von Hoene here. So don't be surprised, she will be taping the discussion. Linda von Hoene is from the GSI Resources Center, and she's going to give me evaluations how I taught today. So behave normally, and then it's not going to be only me and her who's going to be watching this, so no one else will be watching the tape. Okay, so today what I want you to take out of the discussion is how do you check that your finite element solution or that your code is really working, okay? So I have a set of questions, and maybe you can work in pairs, okay? Maybe two of you can think about, let's say, the first 4 questions, and then we can discuss them back. Okay, so maybe you two work together. Does everyone have a partner? Okay, he doesn't have one, so you mind changing seats. I don't like to ask you who are not in this class, right?
The way I checked it was if my hair was getting smaller.
That sounds good. Because that requires knowing
I guess the residual.
And Zohdi like mentioning something like that.
Oh yeah. You got one?
And more smaller. If they get smaller, give them the wires
Yeah.
I know because I got that. It looks really cool. You can do like the square and the square root of like that. Plus of the residual is a measure of the number.
I think that was
And don't you need an analytical set. You need the equation to put it into, right? You don't have the equation. Yeah.
Maybe you're gonna discover the answers for number 1 when you go to the other specific questions. So just put whatever you can think of for number 1, and then while you go solving the other questions, you're gonna find something that's for number 1.
Because I think like because the way that energy node is created, that you're always going to keep working on like it will reduce the definition, right? It works by basically finding the lowest potential image in the state, so you don't forget. You're guaranteed to
Like linear problem is if you have f of a x, it's equal to a of x. That's like yeah. But I'm wondering what's the denominator. Like the result will still be the
I think what's wrong with the classes, they don't really present any like information before. It's just example. You know, it's it's not like, it's never like, yeah, like, here's some definitions and like, here's something. No, it's like, here's an example. And I'm not going to finish, restart at the next lecture. Then you get really confused.
Yeah. Our whole guess solution is linear. The whole guess solution is linear.
Actually, he just came in. Do you have a partner? Okay. Do you mind?
Quadratic.
No.
Okay.
Alright.
Solve the first four questions. How are you? Oh, yeah. Solve your problem in some courses, okay? And then you refine your mesh and you solve your problem again. And then you refine your mesh again and you solve it. So you have 3 different solutions. They might differ from each other. For each mesh and solution, you calculate the energy. Okay? So you get energy estimate for the first one. You get energy estimate for the second one, third one. So you have 3 points. So you plot your energy versus number of elements.
This is the energy norm that we've been doing.
Exactly. And you've been doing it just for one test. And then you so you plot the energy versus the number of elements. And that's going to give you a curve. So it's like a curve fitting. And then you can shoot for the number of elements that's going to give you an energy error or energy that's less than some sort of tolerance. So you can draw lines.
So do you have to use the same like type of element and like constant mesh size for each thing?
So you have learned to be a linear. You don't have to be. Maybe you can take linear versus quadratic elements. So your x-axis would be the number of nodes, but it's not going to be fair to that. So you have to keep the number the same type of elements. So while you're don't think too much about one because in 2 to 6 there are going to be hints for things you can use, and actually section number 2 is going to add something interesting.
And then they're like,
I don't know how useful it is if you do like have to stick to a certain element. Like one of the things Zohdi talked about was like finding something and then just redoing a certain area with the fire mesh.
Right, and being limited to having
I wonder how that's great.
yeah, that might just be like
but why use that?
Yeah, like a query to get the
right. Definitely gives you
It also is more demanding. Did you by chance plot so if you plot the curve,
Wait, what's the string curve?
For sure. But if the time, maybe because they're not going to have yeah, I mean, so that's right. The only reason I this was to have it from Yeah.
And then so
I mean, kind of came in there. I just think about it like in
okay, do you need some time or should we talk about 1 to 4? Okay, let's talk about that. So, can you guys list some ways how you could check that your finite element solution has converged to the actual solution? So what are ways you have tried in your homework, for example? Energy norm. So the energy norm, what does it do? And that's kind of something for number 5, but let's talk about it. So the energy norm, what did you compare? What did you do with the energy norm?
Certainly you need the analytic solution.
Mm-hmm. So you need the analytical solution to get you. So the energy norm was giving us the difference in energy between the finite element solution and the analytical solution.
Yeah.
So one way, when you have the analytical solution, you can compare your finite element solution with it and say, well, it converged. The energy thing, it was comparing the energies between the energy outcome between the finite element solution and the analytical solution. So why do we compare the energy? Why do we care about energy in our systems?
because you can think about it, if you put a load on a system and it causes a deformation, the load puts energy into the system, so the system has to have that much energy in it. So the energy inside the system is different than the energy you put in the system. There's probably something wrong.
So can a system that's in equilibrium have different energy states?
Yes. Maybe. No.
No. So there is only one.
Well, can't you have in buckling a unsteady state and then a
Yes.
steady state?
So that's an unstable thing. But let's imagine we are solving a stable problem.
Okay.
So we would have just one unique energy state, okay? And the analytical solution hits that energy state. So we want to make sure that the finite element solution gives me that same energy state. And if I plot a curve like this, and that's the energy versus that's energy, and that's, for example, a set of solutions, okay? So let's say, so where would be the energy state as associated with the analytical solution? The lowest point. So the minimum energy required to put the system in equilibrium. So the finite element solution doesn't hit this point, but we want to make sure that it's converging to this point, whether from left or right, okay? And some other numerical solution might be here, so they are not giving me the correct energy state. For example, the Galerkin method might give you a solution that is not associated with the minimum energy. Okay, and that's why the finite element solution is a good thing to use, because it physically pushes the system to go to the minimum energy state. Yes?
Can you use the energy error norm if you can't solve the equation analytically?
And then you would just look for the energy made. So the energy norm that you used in your homework was a relative error thing, and you were taking the difference between the energy done by the finite element solution, if we look at UN being the finite element solution, minus del U del X squared, okay? And we're dividing by the energy of the analytical solution. So if we don't have U, so what you can look at is the energy by the finite element solution, okay? So we're not looking at a difference anymore, and then you're solving with a different number of elements. So for a variety of n's, you're gonna look at your energy using this thing here, and then you want to look that the energy would be decreasing as you increase n. Is this clear to everyone? So once you increase your number of elements, your energy, your finite element solution should become good, so your energy state becomes closer to the minimum state. So you would guess that your minimum state is what, for example, if we're plotting this thing here, let's call it E versus the number of elements, N, then you should get something that's decreasing. So whenever you increase N, your energy is decreasing. So you might want to stop somewhere here and say, well, this is my energy state. I mean, the finite element solution is just an approximation. So it's up to the user to decide where the minimum energy is. Okay. Yes. Do you have a question?
Is the two norm necessarily the energy norm? I mean, because like the heat equation, the one norm is the energy norm.
The two norm, are you thinking about the Euclidean norm?
I mean, here we're using the continuous two norm, right?
This is, are you thinking about the Hilbert space?
Yeah, well, I mean, if you have like the absolute value, I mean, in some extent, that's the energy, right?
Yes, if you have to take, so this is something positive, so you don't have to take the absolute value of it. And then to make it be a norm, I forgot here to put the square root thing, okay? So if we're talking about norms, you have to take the square root of this. This is taking into account the first derivative, so it's the first Hilbert norm. So I'm not sure what you meant with this, with the two norm.
I mean, you're saying that's the energy norm, right? But I'm wondering if that's energy norm for all the differential equations or just for, you just call it the energy norm.
It is the energy norm if you're looking at U being a physical quantity, for example, displacement, and if you're taking derivatives. I mean, if you're looking at this being squared, it's mathematically the two norm.
Right.
But why it's an energy norm? Because you're taking the derivative. So the two norm of a vector, for example, is the scalar product of the vector with itself, and you're taking the square root.
Right.
Yeah. So this is mathematically the same thing, but it has a meaning. And the meaning comes from taking derivatives here. So let me explain that better. So if you're taking a vector U, okay? Let's say the vector U has components U1, U2 to UN. So the two norm of U is U, and then there is this two thing here, the two lower index, and you're taking U dotted with U, so the scalar product, and then you're taking the square root. That's a mathematically speaking two norm, okay? But over there, I'm not looking at U itself. I'm looking at the derivative of U, okay? And in multi-dimension, you're gonna be taking the gradient of U. And that's why the thing that you're taking derivatives gives you an energy out of it. Okay, so the energy is not a mathematical definition, but rather a physical definition of this. Okay, so let's see what else can you do to check the convergence of the finite element method. Sarah had something. Do you want to tell me what you?
There's something called the I don't know if it's Richardson method or what but there's this thing that you have three different meshes and a fine, a coarse, and an in-between one, and you use this when you don't know what U of X is specifically, and you'll run it through and you'll get your error and you'll get the number of elements it takes for that, and you'll plot a curve, and so therefore you can get, for this kind of error I need this many elements. So but you need to have a uniform elements for that.
So yeah, did everyone get what Sarah was trying to explain? So what Sarah suggests is you take, for example, three mesh sizes, okay? You take a coarse mesh, a middle mesh, and a finer mesh, okay? And then for each mesh, you solve your problem. Okay, and for each solution, you calculate your error, or your energy error, okay? So then, again here, as we go, so when your n increases, your error would decrease if your code is correct and if everything is correct. So you're gonna get 3 data points. This one would come from the coarse mesh, this one come from the finer mesh, and this is coming from the most fine mesh. combine them by fitting a curve. And then this is going to give you a hint when to converge. So you're going to draw a line, say, oh, I define convergence when my curve is going to go below this tolerance here. Okay? So once this curve hits this one, you're going to say, well, that's when I hit convergence. That's again a user-defined thing. And that's a method that people use. Yes?
How do you know how to fit that curve? Like, how do you know it's that shape? Do you just use like a...
So if you have 3 points, you can use a spline. So it's always, it's up to you how you want to fit it. You can, if you have 3 points, you might want to use a quadratic function. It's not wise to use a line, because you might be missing 1 point. So you want to have the 3 points lie on the curve. Okay. So any other comments? Okay. So number 2, can someone argue why do we use residuals? So this is another thing. So you want to use also residuals to check the convergence. Why do you want to use residuals instead of all the things you told me?
We don't have the analytical solution.
So if we don't have the analytical solution, can we talk about an error that is made between the analytical solution and the finite element solution? No. So we have to see what is available, and the only available thing is the residual. Okay. So in your homeworks, this is what number 4 says. So number 3. So it says, how does the residual behave when you have a linear problem and when you have a nonlinear problem? Did you guys solve a linear problem in your homework 1? Right. So how many times did you have to solve the problem? How many times did you hit backslash in MATLAB? Once. So in one solve, you made your residual become equal to 0. Okay? In a linear problem, the residual becomes 0 in a single step. For nonlinear problem, it takes many iterations. So you start with a guess. I just want you to know this concept. You might not need to solve a nonlinear problem here, but as you go out and work, all the problems are nonlinear. So you have to know if when you're using a black box like Abacus or COMSOL or ANSYS, you should know when it's taking forever, means like it's using different iterations to get to the good solution. So you start with a guess, okay, and then you solve your problem. So solve problem. And then when you do that, you think you're good, but you're not, because you're going to check your residual. So you're going to check your residual, and it's usually something not equal to 0. And it's something sometimes big. So you have to go again and solve the problem. And you do it as many times until your residual becomes something close to 0. It will never be 0, but you might hit the machine epsilon, like 10 to the minus, minus 32. And then you're fine, because the computer says it's 0, but it's actually not 0. There is still an error there. Okay? So that's the only difference I wanted you to take out from here. Okay. So for number 5, I'm asking you to think, do the elements contribute in equal values to the energy error norm in general? How was it in your homework number 1, and how would it be in general? And that's actually a hint for homework number 3. So how did you implement the energy error norm? Like this, for example, the difference between del UN, del X, del U, del X. Element by element, right? And did you guys, maybe you didn't look at the values, but do you think that the difference is the same or not? No. It's different, because it depends on which elements, the node values, right? What else? So the only thing that made this differ were the node values. What else could affect this difference here? If you have, for example, the size of your elements, they were the same, right? Imagine you don't have an equally sized domain. Like you have elements that are big and some are small. So you have that contribute to this difference here. How about material properties? They would introduce, a difference in contribution between the elements. So in your homework number 3, you're gonna look at this value here, element by element, okay, individually. You're not gonna be looking at the entire thing. In homework number 1, you looked at it over the entire domain. For homework number 3, you're gonna look at each element and look what you can do better for that element. So what are the ways to make the energy error norm become better, for example? If you're looking at it at a specific element, what can you change at that element such that this value here becomes smaller?
The shape function?
Increase the order of the element, yes, that's one way. So you change the shape functions. What is the other way where you keep the order of the elements?
Add more elements.
Yes, so you split the element into 2, for example, or into 3. So you make your elements finer and finer. That's what you're gonna should be doing in homework number 3. So splitting your elements until this value here hits the tolerance.
What do you mean by split the element?
For example, so
You mean increase and?
increase the number of nodes or increase the number of elements, but let's say you started with 3 elements, okay? And then you have calculated this energy error norm for element number 1. And you're not satisfied because element number 1 is giving you a huge error. So what you're gonna do, you're gonna split it into 2 elements.
Oh, okay.
So make 2 out of 1. And you're gonna do this until you're fine, you're happy with their error.
On the specific element.
Yes, element by element, yes. So if this element gave you an error that is good enough, then you don't have to split the element. Why increase the system size if you don't have to, right? Okay. Okay, any questions? Let's do number 6 together, and then you can think about section number 2. So number 6, does the quadrature order affect the conversions? Yes. Why?
Well, the higher the order, the better it'll approximate the function there, and so it'll converge.
Exactly. So, so you should do your best at not introducing noise into your error, right? Because you are approximating integrals. I mean, if you would do the integrals by hand, there will be no error in calculating the integrals. So you should use the best quadrature to approximate your integrals and make sure that those integrals will not affect this error here, so there won't be noise. So if you're using a lower quadrature order than needed, then you might get a higher error here, and then a higher error here. So then your conversions will take forever. It will take more, and it's gonna give you a wrong answer such that you need more elements to get conversions. Yes?
So when you say approximation using quadrature, do you mean if you're not using appropriate order? So like if you have a third order system, you're using like 1 or something?
Yes, exactly. So you wanna make your FEM code be the cheapest as possible, but also not that cheap such that it introduces errors.
If you use the appropriate number of points, it gives you an exact solution though, right?
For a polynomial. For a polynomial thing. But we are dealing with polynomials, so you were right. But if you're having sine functions, exponentials, and so on, you want to use the best quadrature order such that it gives you an accurate solution, an enough accurate solution.
In those cases, do we use like a Taylor expansion or something to?
They use, actually in practice, it's always quadrature, Gaussian quadrature.
But if you wanted to approximate like a sine function or cosine or something, would you approximate that as a polynomial?
You can do that, but it's not done that way because it's more expensive, and you have to change your code each time you're changing your functions. So the default way is to use Gaussian quadrature, but to increase the order. You would have flags, or it's non-linear, so let's use maybe 5 points. And you think with 5 points you should be lucky. Okay? Any questions? Why don't you start thinking about section number 2? Remember? Like, what did we take? So I remember there was one problem. We need the displacement field in 3D, and then I told you calculate the strain. And I told you calculate
Tractions are forces with direction. No, stresses with direction.
And what were the tractions?
That's it.
Right? Isn't that what traction is? So the force already has direction. I think traction is a stress and direction.
Okay, so guys, do you remember what tractions or fluxes were? You remember in the mechanics review we did at the beginning of the semester? We encountered something like tractions.
They were like stresses with directions, right?
Yes, stresses
Like
with directions.
A matrix that was had directions associated with it.
So tractions are forces, if you want to think of them that way, but in a specific direction. So if you're having the stresses in your system, you take the stresses multiplied with your normal vector, and you're going to get your traction vector from that. So here we are dealing with a, sorry I didn't specify that, we are dealing with a one-dimensional problem. So do we really have a direction thing? So what is the traction equal to? I mean, roughly, what is it equal to? The stress, okay. And let's imagine we are dealing with a linear material, okay? The stress is given by Cauchy's law as equal to Young's modulus times strains, right? Do you agree? Okay. And then the strains are given by, if I'm giving you the displacement field, first derivative. So roughly the tractions are of the order of the derivatives of the displacement field. And the flux is a more general way, because the tractions are only forces. But fluxes could be derivatives of temperature, derivatives of displacement field, a derivative of a current, you know, whatever you're looking for in your problem. So the flux is a more general way to describe those derivatives. So maybe let me write that down again here. Okay. Let me use this board. Okay, so let's say we are solving for U as a displacement field, okay? How do we get the stresses from, the strains first from the displacement field? Du dx, okay? So epsilon is the strain is equal to del U del x. And the stresses are given by Young's modulus times epsilon. So if you're having a linear material, so E du dx. Okay. Now, the definition of attraction is you're taking the stress matrix, however we only have a stress component, times the normal. In 1D, do we really have a normal? Direction, we don't have anything. We have only one direction, so we don't have to multiply with anything. So our tractions T are actually equal to the stresses sigma. Okay? And sigma is equal to E del U del x. So I can say that the tractions, the stresses are of the order of del U del x. Okay? So if I look at the behavior of del U del x, I can conclude about the behavior of the stresses and of the tractions. Okay? This is about the tractions. However, I have under parentheses there fluxes. Okay? I want you to know this word. Okay? So if I'm not talking about displacements, I'm talking about temperatures. Is the derivative of the temperature with respect to x equal to a force? No. We call it a temperature flux. Okay? But they are mathematically the same thing. It's a derivative with respect to x. Flux is a more general word. I mean, if you're looking at forces, then you call them tractions. If you're looking at temperatures, you call them temperature fluxes. If you're looking at currents, for example, in an electrostatic problem, you're talking about the current flux. Okay? So I think you should be able to do number 1 now.
Yeah, so you said traction would be solution purpose
Yes, if you go, yes.
For us, it's
If you
30
go back to
minutes
that
the
one
H,
down.
but yeah,
So you covered why we use
UI plus 1 minus UI divided by xi plus 1.
Solution as a node, right?
And then that would be
Or you're giving the solution at the node, then it shouldn't really matter. Because the element edge is at the node, so it shouldn't be this continuous.
plus we
It's
behave
based off the solution at the node.
that would be an undefined change.
Then you wouldn't have it. Oh, then yeah, well, you would have problems. Discontinuous.
Basically,
Doesn't really make sense.
Well, it should be static.
No, I was talking about. Yeah.
yeah.
Are you sure?
Why?
If you think about it, because we have a,
This is you as a,
because
it's just
we
a
have a solution between
so
that
find
point
the
and
solution to something
really we
that
solve for
has the value just a-
these points here,
So how
and
do you
then
approximate
the shape function defines the behavior in between.
these
So
functions? So we have these functions
so
and we have the values that we
and our shape functions
So
and
how
our
do you
linear
write the
functions
solution?
basically make it a consistent slope between
So
point A and
what
point
is
B.
the
But that slope information doesn't get translated from B to C.
So you is
I'm not sure if you're quadratic or me, so.
over each other.
Because if you see this, if you remember and you look at your answer would go like this. So this would be at the node.
If you're
This
bending
is
it,
valid over
all
all
the
or
axes
it's
are
valid
taking
over
the carbon.
the other channel. So
And you don't really have
now
a
let's
chance
look
of
at two
like having it
elements
slipping
that
those
I
into
think
the
are
carbons like
and then calculate the flux.
losses, so it's not like they're really, yeah, it actually like, you know, all fibers don't have any elastic deformation. It's all steady fibers. So you really get like no calculation.
How did you define that? How did you take that?
Think about it.
Root of 1 is 1
Okay, so each element have like these, right?
No, that's